Hello, my name is Seth Adams. This is Physics 2211 Lab 2, Motion of a Falling Object. The purpose of this lab is to track an object falling somewhat slowly. This will allow us to determine the effect of drag on the object and how the net force is affected. The track results will then be compared to a computational model on a graph. This lab focuses on three main principles: Newton's second law, gravitational force, and drag force. Newton's second law is force equals mass times acceleration. This can be transferred over to the velocity update formula, where velocity initial plus F net over m times t, or the position update formula, R2 equals R1 plus V delta t. The gravitational force is F of g equals negative mg times the unit vector. The drag force equation equals F of d equals negative b, absolute value velocity squared, times the unit vector. And the net force is F net equals F of g plus F of d. F of g would be the force of gravity and F of d would be the drag force. The procedure for this experiment was to record a video of an object falling starting at v equals 0 meters a second. Import the video in the tracker and track the object's position between a specific time interval. Use the data from the tracker to create a model in VPython to illustrate what Fnet equals Fg would look like in ideal conditions with the same parameters. Use the data from the tracker to create a model in VPython to illustrate what F of net equals F of g plus F of d would look like in ideal conditions with the same parameters. For both models, create a position versus time graph and compare. The initial conditions: the mass of our paper ball was 0.009 kilograms. The ball's initial position was at 0, negative 0.001, and 0 meters. The ball's initial velocity was at rest, which is 0, 0, 0 meters a second. For the system, that would be the ball falling. The surroundings would be the earth. And the major assumption we can make in scenario 1 is that drag is ignored and the x position will be equal to 0. The assumption for scenario 2, use for drag and the x position will be equal to 0. This is the code for no drag. As you can see here, we have Fnet set equal to F of g, and we have it set in the velocity update formula down here in this line, and the position update formula is in this line right here. This is the graph we have for the predicted position versus time after using the no drag computational model. As you can see, the tracker position and the predicted position are not the same, and this could be because the model does not take into effect drag, and so it's going to throw off what actually happens versus the predicted position in the model. This is the code for drag, and as you can see, we have the equation for weight force right here, the equation for drag force, the equation for net force, and then down here we still have the velocity update formula and the position update formula. This right here is our graph overlay of the three positions, and as you can see, the predicted position for drag and the predicted position for no drag do not match the tracker position, but the drag position is much closer than the no drag. For our results and visualized data, the drag final position for the drag model was closer to the tracker position, but the path taken was slightly different. The gravity with no drag was by far the least accurate model. Some errors that could have been made: the center of mass point picking from the tracker because the ball was blurred in the video. Only a few frames were analyzed because it was dropped from a short distance, and the object moved slightly in the x direction. So which model predicts a terminal velocity? The drag model velocity is leveling out, while the no drag will continue to go on forever. The drag model is approaching terminal velocity, but is not quite there yet. When it does reach terminal velocity, F of g will equal F of d, and the F net of that force will be 0. If the object is thrown down, however, the terminal velocity will be reached faster, but the terminal velocity will still remain the same. As you can see in the graph over here, both of the lines look the same. When it is thrown, it just so happens to start at a higher number. Thank you for watching my lab report.